Dear learners, a very warm welcome in the MOOCs of Power Generation Technologies. In this module, we are going to discuss about Otto cycle, Diesel cycle and Duel cycle. I am Dr. Shweta Tripathi, Assistant Professor in Mechanical Engineering from School of Engineering and Technology, Indira Gandhi National Open University, New Delhi. The learning outcomes of this particular module is to understand thermodynamic cycles, to understand air standard cycles and their assumptions, to understand the mean effective pressure and various processes of Otto, Diesel and Duel cycles. So first of all, what is air standard cycle? So before that, let us discuss what is theoretical analysis. So the accurate analysis of the various processes taking place in an internal combustion engine is really a very complex problem. If these processes were to be analyzed experimentally, the analysis would be very realistic, no doubt. It would also be quite accurate if the tests are carried out correctly and systematically, but it would be time consuming also. So if a detailed analysis has to be carried out involving changes in operating parameters, the cost of such an analysis would be quite high, even prohibitive. So an obvious solution would be to take for a quicker and less expensive ways of studying the engine performance characteristics. So a theoretical analysis is the obvious answer for that particular. So this theoretical analysis, as the name suggests, involves analyzing the engine performance without actually building and physically testing an engine. So it involves simulating an engine operation with the help of thermodynamics so as to formulate the mathematical expressions which can then be solved in order to obtain the relevant information. So the method of solution will depend upon the complexity of the formulation of the mathematical expressions, which in turn will depend upon the assumptions that have been introduced in order to analyze the process in the engine. And the more the assumptions, the simpler will be the mathematical expressions and the easier the calculations will be. So the large number of assumptions are better. But again, when the assumptions are so much, the accuracy of the final result will be lesser. The simplest theoretical analysis involves the use of the air standard cycle, which has the largest number of simplifying assumptions. As you all know that a thermodynamic cycle we generally utilize for the practical applications of steam power, refrigeration, we identify a thermodynamic cycle. A thermodynamic cycle occurs when the working fluid of a system experiences a number of processes that eventually return the fluid into its initial state. So a cycle should be there from the process where we have started at that point we have to close also. So generally, if we talk about the thermodynamic cycles, all the cycles have a heat rejection process as an invariable characteristics, and the net work done will be always less than the heat supplied. So generally it is equal to the sum of heat added and heat rejected work done. So the thermal efficiency of a cycle is defined as the fraction of heat supplied to the thermodynamic cycle that is converted to the work. So this is how we define the thermal efficiency of any cycle. Now heat engine, it defined, or we can say that it applies to combustion engines which have a source of energy, the chemical energy which is residing in a fuel which is used in the engine. So any device that is operated in a thermodynamic cycle absorbs thermal energy from a source and rejects a part of it to a sink, and it presents the difference between the energy absorbed and energy rejected as a work to the surroundings, and this device is known as the heat engine. So generally this heat engine is a device that produces work. And how the work is produced? By supplying heat. So in order to achieve this purpose, or in order to produce the work, the heat engine uses a certain working medium which will undergo some processes. What could be those? A compression process where the working medium will absorb energy as work. A heat addition process where the working medium absorbs energy as heat from the source. And an expansion process will be there where the working medium transfers energy as work to the surroundings. And a heat rejection process where the working medium rejects energy as a heat to a sink. And thus the cycle will go on. The air standard cycle is a cycle followed by a heat engine which uses air as the working medium. So here we will take air as the working medium. And since this air standard cycle is the simplest and most idealistic, so these cycles are called ideal cycles also. And the engine running on such cycles are called ideal engines. So air standard cycle is the ideal cycle and the engine which is running on it is an ideal engine. So in order that the analysis is made as simple as possible, that is to make the process simplest, we have to make certain assumptions, as we are assuming that air is the only working medium there. So we have to make several other assumptions also. So what are these assumptions and why we are going for these assumptions? These assumptions result in an analysis that is far from correct and most actual combustion engine process. But the analysis of considerable value for indicating the upper limit of performance means more than this is not possible. The efficiency more than this is not possible. The analysis is also a simple means for indicating the relative effects of the principal variables of the cycle and the relative size of the apparatus that is used. Now the working medium is a perfect gas with constant specific heat and molecular weight corresponding to values is at room temperature. So the various things that we have to assume is depending upon the perfect gas, that how we are going to maintain this perfect gas. We also assume that there should be no chemical reactions occur during the cycle. Only heat addition and heat rejection process is there. Only we are considering heat transfer processes. We also assume that these processes are reversible. Then the losses by heat transfer from the apparatus to the atmosphere are assumed to be zero in this analysis, which is not at all possible, but we are assuming, because when we will consider these heat losses, the calculation will be very difficult. The working medium at the end of the process or cycle is unchanged, as it is at the same condition as it was at the beginning of the process. We are taking air, the heat rejection process is there, heat addition process is there, compression, expansion, everything is there, and then at the end we are assuming that the air is same, which is not possible. But if some add-on will be there, to analyze the process will be very difficult. So we are assuming that working medium will be same or it will be unchanged at the end of the process also. While selecting an idealized process, we always face with the fact that the simpler the assumptions, easier will be the analysis. But it results farther from the reality. And the air cycle has the advantage of being based on a few simple assumptions and of lending itself to rapid and easy mathematical handling without recourse to thermodynamic charts or tables or complicated calculations. On the other hand, there is always the danger of losing sight of its limitation and of trying to employ it beyond its real usefulness. Now comes the piston engine air standard cycles. Piston engine is the engines where the piston is moving. So here basically these engines are for diesel engines, petrol engines, etc. So the cycles described here are air standard cycles applicable to the piston engines or internal combustion engines. Here engine based on these cycles have been built and many of the engines are still in use. Now the first one is the Otto cycle. The Otto cycle, which was first proposed by a Frenchman and was first used on an inbuilt engine by a German Nicholas A. Otto in 1876. The cycle is also called a constant volume or explosion cycle, and this is the equivalent air cycle for reciprocating piston engines which are using spark ignition engine. Generally in a spark ignition engine, the mixture of air and fuel is supplied and then it is ignited with the help of a spark. So here in Otto's cycle, at the start of the cycle, the cylinder contains a mass m of air at the pressure and volume indicated at point 1. So generally the mixture of air and fuel is injected, but we are assuming that the air is there only. So mass m of air at the pressure and volume is indicated at point 1. This piston is at its lowest position and it moves upward and the gas is compressed. Gas whichever was there is compressed isentropically to point 2. Suppose this is your point 1 and this is point 2. So from when the piston is at the bottom dead center, the air comes inside, and when the piston moves upward, the gas is compressed isentropically to the point 2. And at this point, the heat is added, and the addition of heat will be at constant volume for Otto cycle. So this raises the pressure to the point 3 that is shown in PV diagram, and the higher pressure charge now expands isentropically, pushing the piston down on its expansion stroke to point 4, which is again at the bottom dead center. So here the charge rejects heat at constant volume to the state point 1. So the isothermal heat addition and rejection of the Carnot cycle are replaced by the constant volume processes here, which are theoretically more plausible, although in practice even these processes are not practical. So the heat supplied QS, we can say per unit mass of charge, will be given by, we know that heat is equal to mass into C, mass into specific heat into difference in temperature. So here Q supplied will be CV, that is specific heat at constant volume, because the process we are taking is at constant volume heat addition, multiplied by the difference in temperature 3 minus 2, because from the process 2 to 3 we are adding heat. So the Q supplied will be CV into T3 minus T2, because it is per unit mass of the charge, so mass is 1, m is 1. So QS is equal to CV into T3 minus T2. Now the heat rejected, suppose it is QR per unit mass of charge, then it will be given by CV into T4 minus T1. Why? Because heat is rejected when the process 4 to 1 is going on. Now the thermal efficiency, as we know that the network is the output that we are getting and we are supplying heat QS. So the thermal efficiency will be output upon input, which is W by QS. Here W is Q supplied minus Q rejected, because we know that from the first law of energy conservation, we know that net work is equal to net heat. So work generated here is W and difference in Q is QS minus QR. Now let us assume that R is the compression ratio. Compression ratio is the difference, the ratio of V1 to V2. Then efficiency will be given by 1 minus 1 by R to the power gamma minus 1. Efficiency generally increases with increase in compression ratio and specific heat ratio. Specific heat ratio is gamma, Cp by Cv. So from here we can see that if we want to increase the efficiency, we have to increase either compression ratio or increase the specific heat ratio. Specific heat ratio is generally same. So we have to increase the compression ratio. And we can also see from here that it does not depend upon the load, amount of heat added and any initial conditions. It only depends upon the compression ratio and the specific heat ratio. So this specific heat ratio could be different for different fuels. But here we are taking air as a fuel, so it will be same. Now the mean effective pressure. In our previous module we have learned that to see the performance of any engine we need to know about the mean effective pressure. It is that constant pressure which, if exerted on the piston for the whole outward stroke, would yield work equal to the work of the cycle. So it is given by the work that is given from that we are getting from the cycle, that is W, divided by difference in the volume or change in the volume, that is V1 minus V2. So from here we can say that it will be equal to eta into Q into 3. We can replace work done by eta into Q2 to 3. So here it will be eta into Q2 to 3 divided by V1 minus V2. Now when we replace the values V1 minus V2 etc., we will get V1 minus V2 is equal to V1 into 1 minus V2 by V1. And this V1 by V2 is given by R, that is compression ratio. So it will be V1 into 1 minus 1 by R. Now as we know that for ideal gas, PV is equal to MRT. So P1 V1 is equal to MRT. So V1 will be equal to M into R T1 upon M by P1. So here just placing the value of V1 in the previous equation, we will get MEP is equal to mean effective pressure is equal to eta multiplied by Q2 to 3, that is heat supplied, multiplied by P1 into M upon M R0 T1 divided by 1 minus 1 by R. Why we did this? We did this to make it in the terms of the initial state, because for any cycle we know the initial condition P1 T1 we know, and then accordingly as per the ideal gas behavior they will be changed. So from here we can calculate MEP if we know the starting condition and we know the basic values. Now the quantity Q2 to 3 by M is heat added per unit mass, which is equal to Q. So in the place of that we can place Q. So MEP is equal to efficiency multiplied by Q, that is heat added per unit mass, multiplied by P1M by R0 T1 divided by 1 minus 1 by R. Now non-dimensionalizing this MEP with P1, we will get MEP by P1 is equal to eta into 1 divided by 1 minus 1 by R into Q dash multiplied by M divided by R0 T1. So here R0 by M is equal to CV into gamma minus 1. So we will get MEP by P1 is equal to eta into Q dash CV T1 multiplied by 1 upon 1 minus 1 by R into gamma minus 1. Here R is compression ratio and gamma is ratio of specific heats. So MEP by P1 is a function of heat added, that is Q dash, initial temperature, that is T1, compression ratio, that is R, and properties of air, which is CV. CV is specific heat at constant volume and gamma is ratio of specific heats. Now the diesel cycle. This cycle is proposed by a German engineer, Dr. Rudolf Diesel, to describe the process of the engine which was invented by him, which is also called the constant pressure cycle. So this is believed to be the equivalent air cycle for the reciprocating slow speed compression ignition engine. And this cycle has processes which are same as that of the Otto cycle, only the heat is added at the constant pressure. You can see it in the PV diagram also. Here the process 2 to 3 is constant pressure heat addition. Now thermal efficiency of cycle is given by eta is equal to 1 minus 1 by r to the power gamma minus 1 and rc to the power gamma minus 1 upon gamma into rc minus 1. The process for calculation of thermal efficiency will be same as that of Otto cycle. Only we have to concentrate that the heat addition process will be at the constant pressure here. So we will get a new term, that is RC, and this RC is the cutoff ratio, that is V3 by V2, and we can write RC in terms of Q as RC is equal to Q dash by Cp T1 R to the power gamma minus 1 plus 1. Why Cp here? Because it is the heat addition process here is at constant pressure. Now it is seen that the expressions are similar except for the term in the parenthesis for the diesel cycle. It can be shown that this term is always greater than unity. Now where R is the compression ratio and RE is the expansion ratio. So R is the compression ratio, that is V3 by V4. RE is the expansion ratio, that is V1 by V2, and RC is the cutoff ratio, V3 by V2. And this RE and this R, that is this RC cutoff ratio is equal to R by RE, that is compression ratio to the expansion ratio. Now we can write the mean effective pressure formula for the diesel cycle. Just we have written for the Otto cycle in terms of eta, Q, gamma, CV and T1. Why in the terms of these things? Because we want it in the terms of T1, because we always know the initial properties or the initial parameters or the properties which are at the initial moment. So here MEP by P1 will be equal to eta Q dash by CV T1 divided by 1 minus 1 by R into gamma minus 1. So we can write the MEP in terms of gamma, R and RC also. MEP by P1 is equal to gamma R to the power gamma multiplied by RC minus 1 minus R into RC to the power gamma minus 1 divided by R minus 1 into gamma minus 1. If we give this expression for in terms of MEP by P3, it will be MEP by P3 is equal to MEP by P1 into 1 by R to the power gamma. Now comes the dual cycle. An important characteristic of real cycles is the ratio of the mean effective pressure to the maximum pressure. Since the mean effective pressure represents the useful pressure acting on the piston, while the maximum pressure represents the pressure which chiefly affects the strength required of the engine structure. So in the constant volume cycle, it is seen that the quantity MEP by P3 falls off rapidly as the compression ratio increases, which means that for a given mean effective pressure, the maximum pressure rises rapidly as the compression ratio increases. For example, for a mean effective pressure of 7 bar and Q dash by CVT1 of 12, the maximum pressure at a compression ratio of 5 is 28 bar, whereas at a compression ratio of 10, it rises to about 52 bar. So real cycles follows the same trend and it becomes a practical necessity to limit the maximum pressure when high compression ratios are used in an diesel engines. This also indicates that diesel engines will have to be stronger and hence heavier also, because it has to withstand very high peak pressures. So the constant pressure heat addition achieves rather low peak pressures unless the compression ratio is quite high. In a real diesel engine, in order that the combustion takes place at a constant pressure, fuel has to be injected very late in the compression stroke. Practically, when it is at the top dead center, then only the fuel should be injected. But in order to increase the efficiency of the cycle, the fuel supply must be cut off early in the expansion stroke also. So both to give sufficient time for the fuel to burn or for the combustion, and thereby increase combustion efficiency and reduce after burning, but also reduce emissions. So such situations can be achieved if the engine was a slow speed type, so that the piston would move sufficiently slowly for the combustion to take place despite the late injection of the fuel. So for modern high-speed compression ignition engines, it is not possible to achieve constant pressure combustion. Fuel is injected somewhat earlier in the compression stroke and has to go through the various stages of combustion. Thus, it is seen that the combustion is nearly at constant volume, which was in the spark ignition engine, that is Otto cycle. So here the peak pressure is limited because of strength considerations. So the rest of heat addition is believed to take place at constant pressure in a cycle. So this has led to the formulation of the dual combustion cycle or dual cycle of combustion. In this cycle, for high compression ratios, the peak pressure is not allowed to increase beyond a certain limit and to account for the total addition. So the rest of it is assumed to be added at constant pressure, hence it is named as limited pressure cycle also. So the efficiency will be given by eta is equal to 1 minus 1 by r to the power gamma minus 1 multiplied by. Now here the constant pressure cycle, we have to take those things also and the things for the constant volume cycle also. So to obtain MEP in terms of the cutoff ratio and pressure ratios, pressure ratio is also there. So we have the following expression. So when we see the diesel cycle, only this RP terms is added here. RP is pressure ratio. So eta is equal to 1 minus 1 by r to the power gamma minus 1, which was for Otto cycle, multiplied by this particular component, which is for the dual cycle, which is Rp into Rc to the power gamma minus 1 divided by Rp minus 1 plus gamma into Rp into Rc minus 1. Now MEP by P1. So this is gamma into Rp into r to the power gamma Rc minus 1. This is the first component. Second is plus r to the power gamma into Rp minus 1, and then minus r into Rp into Rc to the power gamma minus 1 divided by r minus 1 into gamma minus 1. So for this dual cycle, expression for mean effective pressure by P3, ratio of mean effective pressure to the P3 is given by MEP by P3 is equal to MEP by P1 into P1 by P3. So we can write an expression for Rp, the pressure ratio, in terms of the peak pressure, which is a known quantity. So this Rp is P3 by P1 into 1 by r to the power gamma. We know the pressure ratio, we know P1, we know r gamma, so we can calculate P3 from here also. And if we know P3 or by P1 and gamma value we know, r value we know, so we can calculate that what will be the pressure ratio for this. So we can obtain an expression for Rc in terms of Q dash and Rp and other quantities, which is like this. So here Rc is equal to 1 by gamma and two components are there which will be multiplied by 1 by gamma. One component is gamma minus 1 and another one is q dash by Cv T1 r to the power gamma minus 1 divided by Rp. So we can also obtain an expression for Rp in terms of q dash and Rc and other known quantities. So here Rp will be equal to, in numerator we have q dash by Cv T1 r to the power gamma minus 1 plus 1, and in denominator we will be having 1 plus gamma Rc minus gamma. So this is all about the dual cycle. Now let us summarize. We have discussed about the Otto cycle, diesel cycle and dual cycle, various processes of Otto cycle, dual cycle, diesel cycle, and how to obtain efficiency of these cycles, how to obtain mean effective pressure, how to obtain the ratio of mean effective pressure divided by P1, ratio of mean effective pressure with the initial pressure, and ratio of mean effective pressure to the higher pressure also. We have initiated it with the definition of the air standard cycle, thermodynamic cycle, how we are going to achieve various parameters of air standard cycle, what are the assumptions we have met for making it an air standard cycle. Thank you very much.